Okay, let's begin.
Yeah.
So it's my utmost pleasure to welcome Saurabh to AI2 and to Seattle in general. He'll also be at UW tomorrow, showing some new results that he's computed tonight. Saurabh is an assistant prof at UIUC, formerly a PhD student at Berkeley. He does lots of fascinating work with real robots, and I've been excited to hear about some of his latest work with our very own lovely stretch robot, opening
Yes.
cabinets and doing all kinds of fascinating things. So, take it
Okay.
away.
Yeah. Thanks a lot for the very kind introduction. Thanks a lot for having me here. It's great to see lots of familiar faces. So going to talk about robot learning by understanding egocentric videos. And so when we think about learning in computer vision or NLP, we think about training models on broad, large, and diverse internet scale datasets. But when we look at policy learning in robotics, we are looking at papers which are training models often on a handful of objects in a handful of environments, right? And this trend has not changed over time. I think things have scaled up, but it's still small scale models trained on small scale data. And this is for good reason. Sparse reward RL is challenging. What that means is you need to have an expert who can teleoperate the robot to collect data, but teleoperating robots is slow and difficult. And there are practical considerations with taking real piece of hardware out in the world in order to collect data. So the question that the subfield is right now facing is how can we scale up robot learning to get the full benefits of machine learning, right? And over the years, many answers have arisen. You could do self-supervision, which for certain class of problems, take the experts out of the picture, so you can collect data more efficiently all the time. You can scale up data collection by using arm farms, so multiple arms, multiple robots capturing data in parallel. You could take robots, put them in homes, get more diverse data that way. That can help. You can simplify data capture setups so that you can take them more easily out of lab, collect data that way. You could also do sim to real, and that's another way of scaling it up. You can train on lots and lots of environment steps in simulation, and that would be helpful. Now, I'm not going to talk about any of these things. I think there are certain limitations to each of these things. Sim to real helps, but you first need to do real to sim in order to bring something to simulation, and then you need to deal with sim to real in order to get that policy to work in the real world. For certain problems, this makes a lot of sense, has been done successfully. If you look at the top row, all of these things are helpful, but it's still not helpful. These are not sufficient to take things really to the scale at which we're used to seeing learning in machine learning, in computer vision and NLP. What I'm going to talk about today is we'll talk about scaling up robot learning through observation of other agents solving tasks, right? And this is going to be a talk about using videos for doing this. So in this case, videos of people doing actions. And why might we be interested in this? We do it as adults. I'm trying to do something. I can look up something on a video and online, and I can try to learn from there. But it's a crucial part of child development, and has been put very eloquently by Alison Gopnik in one of her popular books, The Gardener and the Carpenter, where she says nearly all animals, even slugs, can learn from trial and error. Smart animals such as crows and primates can also learn by observing others. As we have seen, human children take learning through observation and imitation to a whole new level. They use imitation pervasively to figure out how the world, other people, and their cultures work. So we're going to start with this. This is what we are going to try to do in this talk. In particular, I'll focus on egocentric videos. You could also work with exocentric videos, but I'm going to work with egocentric videos. And they take this form where, let's say a person has mounted a camera on their head and they're walking around in different kinds of environments. So you can get data of this form, or for navigation, or you could actually also get data for manipulation tasks. So in this case, someone is wearing a camera and they're doing things with them, with things in the kitchen and so forth. Okay, so while there is this motivation that I said that, okay, children learn from observing others, we can also ask a more practical question. What is it that we can learn from these videos, and how, and in what ways is it hard? So let's take a look at that. How can egocentric videos aid us, right? The very first thing is they can offer larger variety, larger visual diversity, which might provide good generalization, right? So you have, here I'm showing some snapshots from this Ego 4D kind of data sets. mounting a camera on your head and collecting data is much easier than taking a physical robot out and collecting data. So you can get the benefit of scale and diversity through that. Second, if you happen to be lucky, you can actually find demonstrations for things that people are actually doing, for things that you are actually interested in. So let's say you're interested in training robots to open locks. There's a small clip over here that I'm showing where you can see, this person trying to open these kind of locked cabinets and so forth. So this guy rotated this, then there's another thing inside. And so if you're in the business of figuring out how you can open like these kind of things, there are some demonstrations. You don't have to discover the solution. You can see what someone else is doing and perhaps try to copy. There may be situations where you're not so lucky, where you have demonstrations for things which you are not directly interested in doing yourself. In that case, videos still offer me an opportunity to learn. It shows me what the world is like and how it works. And even though I'm not interested in this task right now, or the whole task that this demonstration is showing, but I'm interested in a subset of it, and I can still repurpose what I'm seeing, right? So in this case, you have this person opening a cabinet. It gives you this information that, okay, the cabinet, I open it by grasping at the handle. You can see what is the effect of this action and so forth. Here's another video clip, again from one of these data sets. And you might not, it's just showing the different ways in which things can go wrong. The cable can get stuck, and the way you get around it is by lifting the table up and then, getting the wire and so forth. Right. So there is an opportunity over here that egocentric videos can help me learn it simplifies the problem in a number of these ways. But there are also challenges, right? So there's embodiment gap. The actions, the capabilities of a human may not be necessarily matched with the robotic platform that you have, right? Or there may be embodiment, there will be gap in like the sensors that you have. Videos don't come with motor labels, right? So if I just have a video, I don't know what action is the human taking and how to map it to robots. The goals and the intents of people are not known. The demonstrations might not be optimal for what you want to do and so forth. So learning from this kind of data might not be as straightforward. So it also poses some challenges. To mitigate some of these challenges and still be able to use video data for learning, what we are going to do is we are going to adopt, we're going to learn something from what has been done in natural language processing, or is one way of thinking about natural language processing, which is to learn at different levels of abstraction. So this is a diagram from classical natural language processing textbook, where you're trying to translate some source text into some target text. And you can think about translation at lots of different levels of abstraction. You could translate at the very abstract level, which is you take source text, you analyze source text to get to abstract meaning. Now, nothing has to be translated in abstract meaning, but you need to figure out how to render it in the other language, right? So you can go up this triangle and come down. And over here, what you need is large understanding of what happened and large understanding of how to actually render it out, right? You could also do direct translation, which is you're translating word by word or phrase by phrase. And if you do this, you need large transfer knowledge. You need to see what particular phrases in English mean and how to map them to French phrases and so forth, right? So there's a trade-off over here, and you can actually also transfer somewhere in between, right? You can convert your text to parse trees. You can transform the parse tree, and then you can generate text using that. So we are going to take inspiration from this, and we are going to look at transferring across different levels in a control hierarchy, right? So on the one hand, I have humans. On the other side, I have robots. Humans express their actions in terms of muscle tensions. Robots have motor torques. But even though you have muscle tensions at the very low level, there's this hierarchical decision-making process that you have macro actions, you have some skills, you have some sub-goals, you have goals in the world. And you have very much the same analogy from language over here. You can do human behavior analysis to go towards these different abstractions. And then you have the same process on the other side where you're generating robot behavior, right? And depending on the amount of gap I have in goals, embodiments, and what we can observe in videos, we might benefit from transferring at different levels through this pyramid, right? So I might not be able to directly map from muscle tensions to motor talks, but I can do some amount of human behavior analysis, transform that towards what a robot could do, and then render that behavior out on a robot, right? So I'm going to work with this triangle picture. I'm going to show you different examples of information flow through this triangle through case studies in navigation and manipulation. I'll start off with certain case studies in navigation. I'll show you a couple of examples there, and then I'll transition to talking about manipulation. Right? Okay.
Can I ask you one question? So we're still talking about ego, or
I'm still talking about egocentric.
because you started by saying I can learn by either do things or watch others do that thing. So when I do things, I learn from ego. When I watch others,
Yes.
it's not ego.
Yes. So I don't have a. I think certain things are easier in egocentric views, but you're right that a children doesn't have an egocentric view of what the adult is doing. Perhaps.
Yeah.
Spot on. Yeah. I'm
But you're
doing
gonna
that
still stay all the time
with ego.
with ego. Please.
I'm going to do everything with ego. We can come at the very end and see why I did not choose to do it. Excellent question. Okay, so I'll start with navigation. I'll quickly show you what we have done with navigation and then move on to manipulation. So what do these videos tell us about how we can navigate? I'm going to argue they tell us where you can go from here and how. So if you have this video snippet, I did not record this in my hotel yesterday, but yeah. So you have this person going out from this place. If you see this video, you can now essentially reason that at this location in this image, it is possible for me to go out and turn left, right? This is a thing that I can do. So I can answer this question, where can you go from here and how, right? Of course, we need to do it. So this is one kind of thing we can learn from videos. Another kind of thing we can learn from videos is what is next to what, right? So here's another video, and this is not a video from my place in Champagne, but you can actually, you've gone around, right? Just this video snippet. You can actually, at this point, if I were to ask you a question, where is the couch likely to be? You can actually answer it that, okay, it's around the corner over here, right? So these videos can actually help us learn both of these aspects of navigation. So let me show you how we actually do this. So this is some work that appeared a little while back. So if there are some challenges over here, right? So the first challenge is if you have a video of this form, it does not come with motor labels, as I said, right? I don't know what action the robot should take. Second, it's possible to do multiple different things at a particular location, and intents are not known a priori, right? And I'll tackle these problems. I'll show you how we tackle this problem. So we are going to do this thing, which I'm going to call action grounding via inverse model. And I'm going to tackle the second issue by jointly mining for intents using a latent variable model. Right? Okay, so in some more detail, this is what we are going to do. I'm going to learn an inverse model. An inverse model is you take a robot, you execute random actions on it. You get IT, AT is action you execute, you get IT plus 1. You train a model which takes in nearby frames and tries to predict what action you took, what was the intervening action. So this is an inverse model. Now, I can take this inverse model and I can actually run this on the video that I have, right? So I have multiple frames of a video. I can actually run this inverse model and I can label it with the actions that take you from one frame to the next, right? So my actions were missing. I can now do this recipe in order to get the action labels, right? So this is a simple way that works out for navigation kind of problems. Okay, so now I have a setup which looks quite similar to what we are used to. I have images, I have actions. And now I can start training policies which take in images and start spitting out actions, right? And so this is what I'm showing you over here. I can take these images, I can have a recurrent policy in this case, which predicts the action that the agent should take. This is where the second problem comes and bites us. If I'm at this particular location, I could be going straight up ahead, or I could be turning right into the doorway. And a priori, I actually don't know which of these intents I'm going to exhibit. What I'm going to do to tackle this problem is I'm going to peek into the future. I'm going to see what this agent actually did, abstract that out into an intent. So in this case, it's a discrete intent, and condition the policies that I'm training on this latent intent that I'm going to model. I can actually also train another model, which I'm calling an affordance model, which can predict this latent intent, right? Yeah, so if I take my videos, I do this process with them. What I get as a result of this is some subroutines, which are low-level skills that the agent can execute, and also this affordance model, which tells me where can I invoke these skills, right? Okay, any questions? Okay, excellent. So here are some results. So you can take this kind of learning, you can try to see what different subroutines or skills did I learn. So in this case, I'm placing this robot at different locations, and you can execute this subroutine 1. And what it exhibits is turn right behavior, that this can be where it is, getting some view, and it can actually execute like a turning right kind of a behavior into a room. Here's another subroutine, which, as you can expect, it learns to turn left into a room, and so forth, right? And again, it can do this in lots of different varied settings, and so forth. You can also visualize the affordance model. So in this case, it is this turn right affordance model. It tends to prefer things which have an opening to the right. So this can actually infer that, okay, at these locations, I can actually invoke this turn right subroutine. Here is again like a turn left kind of a subroutine, which again, it affords, these locations afford a turning left primitive. So we can actually start using these in different ways. So in this case, I'm going to just compose my subroutines and affordances by just at each location, figure out what subroutines can be invoked, invoke that subroutine, and keep doing that over and over again. And if I do this at random in an environment, what you see is you can actually start exploring this environment quite well, right? These are comparisons against two works which are not using video data for bootstrapping this process. They are just vanilla skill discovery methods which do not assume access to videos. And what you can see is you can actually explore much better than these past approaches, right? We can actually also use these subroutines and affordances for hierarchical RL. Yes.
I have two quick questions. One, here, when you say it's better at exploration, how are you measuring that? Is that just the amount of area you cover?
Yeah, so we are measuring like the maximum distance you've gone from where you started from and how much you're able to cover across episodes. Yeah.
And then the second question is more of a detailed thing. So between part 1 and part 2 a few slides ago,
yes,
you had a model that was taking in 2 different images, producing one single action. And
yes, inverse model. Yes.
Then that was the inverse model. And then how is that connected to the second one? Are you just initializing your policy with those?
Yeah, so this inverse model is only being used to label the data. So a hat is the.
Oh, I see. And then you throw it away afterwards.
You throw this inverse model out. Yes, we're not using it. Yes. Good questions. Yeah. Yeah, so we can actually start using these. So I'm going to do hierarchical RL with this. There is a meta controller which you can initialize with the affordance model, and there is a skill that you can initialize with the sub policies that you have. And now what you observe is you can, because it has already learned basic of how a mobile robot can move around. You can actually you see faster training in terms of simulation, right? So what you get is 4x faster training in terms of in this case a sparse point navigation problem. You can actually learn much faster than I guess the strongest other baseline we found was initializing these hierarchies from ImageNet or like these other skill learning methods which are down over here, right? Yeah.
When you learn this inverse dynamics model, I assume there are some actions which are non-realizable for a given hardware, like looking down or looking up if you have a fixed camera. But you're still training the policy to produce that, and it's still able to produce this action. So what?
Yeah, so that's an excellent question. I think these inverse models are trained in the robot action space. And because it has access to both these images, I think these models generalize better than just a policy, because it kind of the answer is there in the next image. You could also do structure from motion and get them geometrically and then map them to your action space. Both are options. Yeah.
So could you explain again how the subroutines are determined? Is it you have a way to predict the intent?
Yeah, so it's all learned jointly. It's basically trying to minimize this particular loss that you have in terms of, you're trying to predict your actions properly. And you can only predict the correct action over here if you have a consistent intent being passed into the network. So in some ways, you can also think of this as I clustered the different behaviors I have, and I learn a different policy for each cluster. That would be another way of thinking about this. Yeah. Yeah.
Similar to the subroutine, how subroutines are determined and how the thing has an intent. So like if you're trying to find a house, like the whole trajectory is finding a house, and you make one left turn and one right turn after, it seems like each left turn and right turn are separate subroutine.
Yes.
For the whole trajectory, the intent is to do it. So how are these
pieced together?
So these are all trained whole trajectory, including 2 different turns, or
Yeah.
as one.
Yeah. So the way we are doing this is it's going to be a composition of these things, right? So this policy, what it is going to do is it will sample an intent. So so you're going to do RL with this, that the meta controller should do the right thing and this should do the right thing. So what it's going to do is I sample an intent, I execute that for a few time steps, and then I resample, I'll execute it using the sub policy, and then I'll resample a new intent and keep going that way.
So if you could redo this in 2024, would you pre-cluster with like some white pair encoding or something like that too? Because turn left, turn right, semantically meaningful, but maybe operationally inefficient. Maybe it is go 3 steps, take a right. And
Yeah, so these are turn left, turn right are quite flexible actually, right? So that's kind of what I was trying to show with this picture. The same, too much animation. The same subroutine turns right at different starting points. So it's adaptive. It's not a predefined, right? It can do that across different initializations and all of that, right? So it's intelligent in that way. If I were to redo it now, what would I do? I would do the same thing. I think there are other papers which have come out, like modeling K modes in behavior cloning. I think diffusion is another way of doing this that might just model it inherently. I don't need to do a separate latent. I guess a diffusion is a latent variable model as well, to the extent that it can produce different, cover the full form. Yeah.
Yeah, I'd also played around with something similar to this, and I found that even when using relatively low dimensional sort of implicit space, it made the imitation learning problem too easy, because it could just, even from very low numbers of dimensions, it would just decode the actions that it would.
So in this case, we're using discrete intents.
And is it like how many?
4.
Oh, okay.
For navigation is like a very small number. Yeah.
How do you determine the number of actions per intent?
It's we just pick 10, but you can also think about, can we segment out trajectories such that they're easier to learn? And there's also work on that kind of a problem. Yeah, it makes learning harder, but what you get out of the learning might be more useful.
On a related question, isn't the intent for the whole video?
It's intent for each 10-step action, 10 steps. In this case.
But in the real world, like, we have an intent for the entire episode.
So I'm basically saying intent is low, like short time horizon intent. Yeah. Okay.
We plan not to let you go finish.
Yes, you can come to the continuation of this talk tomorrow. Yeah.
I get to the opening the toilet seat soon.
Yes. Okay, I see. Okay, so here's the next piece, which is what is next to what? How can you learn that from these videos, right? So the input over here is egocentric videos again, and what we are trying to learn is semantic cues. We are not there at lifting the toilet seat yet, but we are trying to find one. So we are. It's like you want to learn semantic cues, which are indicative of objects that you're trying to find, right? So in this new restaurant that you just went to, how do you find the restroom efficiently? I guess, right? So this is another thing that we are trying to learn, and again, it's again the same thing here. You have these 2 challenges that I talked about before, but then also the depicted trajectories may actually not be may not be optimal. So what we are going to use is we're going to use Q-learning to learn optimal behavior for suboptimal data, right? So they're not too different. I think the action grounding part is the same. What I get after this action grounding is IT, AT, IT plus 1, AT plus 1, and so forth. And I'm going to do Q-learning with this. I think this audience doesn't need an introduction to Q-learning. So this is what I have, IT minus the sequence of images. I do action grounding with my inverse model from before. And then I'm going to do goal labeling, which is I'm going to run an object detector on these frames trained on Coco, and I'm going to get whether there was a bed in this image or not, right? And I can now piece these together into Q-learning quadruples. And I'm going to just do Q-learning with this, and I'll essentially get this function Q star, which is the optimal Q function for an image given action, comma, class label. And this, I'm going to take a max over A. And what this tells me is if I'm interested in looking for a particular object, what image scores highly under this, right? So the value function that can implicitly learn semantic cues for seeking objects. So maybe I'll start with giving some intuition why this process might work. So again, going back to this video, if I have these different frames and I'm trying to see a couch, look for a couch, this frame is actually quite a good one to look for a couch. You already see it. You can actually go towards it quite easily, right? This frame is actually quite good as well because you have this particular object that you're seeing. I mean, it's clipped, but it's pretty good. What I'm going to argue is that this frame is actually also quite good for finding where a couch is because of this co-occurrence between these two objects, right? What I'm observing is this co-occurrence that these televisions are kind of next to couches, and here I'm seeing a television, and what that might suggest is going to the television and then trying to look for a couch, right? And we are not doing this explicitly. We could have done this explicitly. We are just doing Q-learning, which is trying to estimate, roughly speaking, how far is a couch from this image, how far is the couch from this image, and so forth. And these kind of cues automatically get learned, as I'll show you in this particular slide, right? So in this case, here's the panorama, which I take, and now I'm visualizing the value function for different classes. So chairs, couches, dining tables, also beds and toilets. The chair, couch, and dining tables, it's not surprising that it's has a high score over there in that corner, because you kind of can see the couches and the dining tables already, right? What is more interesting is that even for objects that you're not able to see, it has the right it has a high prediction to where it should be, right? So what it has kind of learned is that I'm not seeing a bed over here. Bedrooms are typically next, you have to go down a hallway in order to get into a bedroom. So it's having a high score over here that, okay, go straight and then you might find a bedroom over there, right? So this is the value function which predicts nearness to goal given an image, right? And this is another visualization in the top view. This is for finding a dining table, and you can see that it bleeds out nicely from the area of interest. So you can use these learned value functions for semantic navigation. So you can do hierarchical. What we are going to do is we are going to do a hierarchical policy. It has a high-level policy which decides where to go and emits a short-term goal. The low-level policy takes the short-term goal and executes the actual actions that you need to take to get to the target location. What we also do is the high-level policy builds a topological map that stores what we have seen so far and what are promising directions of exploration, right? So these are the past nodes. This is where you are right now. From each of these nodes, I'm going to render one of those panoramas out, and I'm going to score how likely is it to find an object in a particular direction in each of these panoramas. That's what I'm showing with you with these blue dots. These are value predictions. And at each time step, what I do is I sample the most promising previously unexplored goal. I sample that as a short-term goal. That is my delta pose, and I now pass that on to my low-level policy, which in this case builds a map to do it. We could have used our earlier work to do it as well, but in this case, we are just using something very classical. And this outputs an action, and this returns flow back to the high-level policy. Okay, these are some results. So this is a little bit dated at this point, but the point I'm trying to convey is by starting to use videos, so ours is this 53 number that you're seeing over there, you can actually start off very good. So there's no training. I mean, there's training of this value function that is involved. Other parts are handcrafted. And you can actually see that this starts outperforming imitation learning and reinforcement learning combined with imitation learning, which is basically these two lines with very little frames of direct interaction. What we have done is we have been able to use video data in order to learn effective strategies for finding objects in environments. Other baselines over here are more versions of classical baselines, which it turns out do quite a bit better than purely learned methods at that time.
These are trained on different data, right?
Everything is trained on the same data, habitat. This is experiment is in habitat. In fact, we suffer here from real to sim gap because we trained our value function on YouTube videos and we're testing it in habitat, which has lots of artifacts. Yeah, so I think I'll come back to this triangle. What I showed here for this semantic navigation task, there was something that I was starting from human actions. I kind of abstracted it out into macro actions, and then I did some learning. And what I did was I did something handcrafted to actually render that behavior out in the world, right? You could ask the question, could I not have just, and that gives me some performance. So this is on the validation set. You could also ask this question, what if I got rid of this hierarchy? What if I directly tried to map human actions to robot actions? And we have tried that we're doing that in multiple different ways. Using this hierarchy, using this topological map stuff to keep track of what has been seen, what has not been seen, actually is quite important in order to get this to work well. Because if you just start doing imitation learning here, you have to build like a recurrent model which can keep track of what has been done before in order to advise the next action. And that becomes difficult to learn purely from video data, right? But this hybrid approach where you're learning some things from videos and then marrying it with some classical topological map-based reasoning actually helps quite a bit, right?
Can I ask honest question again here? Do you think this results hold for 24?
I would think so. So if you look at leading systems, so you look at this paper called Navigating to Objects in the Real World last year, it had comparisons to imitation learning. It had comparisons to that was the modular system. I'm not involved in that work. It was a modular system which was disentangling learning where to explore and how to get there. And that actually gets quite good performance. They have extensive real world comparisons. They're also comparing to a method which is doing imitation learning and doing sim to real, or doing reinforcement. Actually, it's comparing to reinforcement learning and doing sim to real on that. And the key hurdle there ends up being that things that have been trained in simulation don't transfer to the real world because of the artifacts in simulation. Now, that work is predates PwnProc and so forth, Proc third. I don't know what the situation would be with that. But I think this disentanglement between separating the high level and the low level has some merits, and I would say that.
Can you briefly describe the videos that you trained on?
The videos are coming from a YouTube channel which has real estate tours. So these are people trying to sell their houses, and you record a video to give people a better sense of what your house looks like. So there's a bunch of these kind of videos that we have trained on. These are biased towards North American homes because these videos were largely collected in North American homes. There's no homes from India, for example. So this has bias of that form. But we did not curate the videos in any other way. These were continuous. What we were benefited from were these were continuous video streams.
Also curious, your formulation using the real estate tours, your formulation was that the goal was a particular object, when by definition that is just a tour, it's not seeking a particular object. Did you find that that introduced any weird?
So that's, I think, where Q-learning comes in. The more random transitions you have, I think Q-learning requires a technical condition that you have to explore all the environment. And maybe that is why it actually worked for us. If it was very goal-directed behavior, then it would not know what to do if you were not on the path to the goal. But we don't know for sure. To me, the exciting part, yeah.
I was going to ask, so my brain, not much embodied AI experience, the obvious way to do these videos would be to train like an image encoder on them with some unsupervised objective. And presumably with like next frame prediction, they'll implicitly learn, I can turn left here, there's a couch nearby, these kind of things. And then you just train the model on top of that. So
that's another very good idea. I think what we are gaining on top from there is Q-learning is actually trying to do long-term reasoning as well. That I am not looking at the couch right now. If you do next frame prediction, then the couch should be visible in the next frame. But it could be multiple frames out, and I can still get a reasonable prediction for where to go. Because Q-learning is in some ways doing this dynamic, like the Bellman equation update can propagate information longer through time. You could ask that, okay, I can train a multi-frame condition model. I have an image and I have multiple actions. That would work too. Yeah.
Is that overkill for finding an object for navigation?
Good question. I have my answer. You can do detection seeker, which works quite well. So this is just saying, okay, I'm looking for an object. I see it, I beeline towards it. You get like, I think, relative 10% improvement over here. And this is consistent with what others have reported that, a strong exploration baseline, you can do about 10% better than that if you have semantic priors built in. Right? You're right. I mean, if you're not after this 10%, then you could do something classical and work quite well.
And looking at your Q function, the inside of your Q function, do you think you've learned this higher order relationship between objects?
I mean, that's hopefully why we are getting improvements. Yeah.
You could have visualized it.
Yeah, we visualized it in these kind of forms that, if you look for where to find an object, it does correlate with intuition that you have. And there are more examples in the paper, right? So in this case, you're not seeing a bed. It is preferentially pointing towards, okay, this hallway is the better one to go into, even though you're not seeing the object. Here's another picture which shows this. I mean, this is for finding a dining table, and you kind of learn that if you're in the living area, dining table is close by. If you're not, then go somewhere else.
The 10% gain you saw was an SPL. Is the same true for
success rate?
Success rate, yeah.
I am forgetting probably on SPS. Yeah, I think a softer metric you will see more improvement. Success rate success rate, you see an improvement because the episode ends. So if you're not efficient, then you will. Yeah, and the numbers are in the paper. Excellent questions. Okay. All right. Let's see. Let's replan. I have 20 more minutes. Okay. Yeah. So I think the talk has this form. I can end wherever. So I'll keep going. Yeah. So VLV has two shortcomings as general solution. Transitions need to be labeled with the inverse model, and we use a task-specific low-level controller in order to get it to work. We have looked at this question: can intelligent behavior just be derived from undirected observations? ST plus 1 RT. I mean, the answer is not very exciting. I mean, we have a paper which you could read if you like to. What I instead focus on is what can we do for manipulation, right? So I'm going to transition and talk about that in the remaining time. So manipulation is a much harder problem. I think there's embodiment gap becomes much more significant, and lots of things are harder. So I'm going to start with some attempts at doing this and where we are, and I'm open to feedback. So one of the things we have looked at for manipulation is interactive object understanding. Given an image, I want to be able to understand what sites can I interact with in this image. How do I interact with those particular sites? I should use this kind of a grasp, and what happens when I do, right? I would like to be able to extract these kind of understanding when I'm trying to do manipulation, right? Now, the reason I like videos for learning these forms of things about objects is because if I hit the play button, I actually get the answers to all of these questions, right? If I can somehow use these, I kind of figured out, okay, you approach the handle, you approach it with this kind of a grasp, and when you open it, you actually see what is inside a cover, right? So in some sense, the answer to these questions are there in the data already, right? And that's kind of what we have tried to do, which is we're going to learn through observation of human hands interacting with the world. So human hands in egocentric videos are informative. Attending to hands localizes and stabilizes active objects of interest. Hands show where all can be interacted in the scene, and analyzing the hand and how it is interacting with the object might reveal information about the state the object is in and how to interact with it. And it's really quite simple. What we are doing is we are going to use off-the-shelf models that can understand hands and what they're doing in images, and we're going to learn from that, right? So we have this image, we have models which can detect hands. We can also detect objects of interaction. So in this case, this particular object has been interacted with. I can actually run some sort of a graph classifier to figure out what graph am I exhibiting. I can get this kind of information from off-the-shelf model, so a prismatic graph. And what I can do is I can start creating training data for training the kind of things I want, right? I take this image, there's a patch around the hand that has been detected. I mask out the hand. And now what I try to do is I have a model which tries to predict whether or where is the hand in this image, right? So given the context, it needs to be able to predict where is the hand in this particular image. You can actually also ask this question, can you actually grasp, where can you actually grasp, what kind of a hand pose can you use when you're interacting with the object over here? So you can actually just do this. I think this is what it leads to. You can, again, these models are trained on the Epic Kitchen dataset, and you get visualizations of this form. What this learns is you are likely to interact with these things like handles. So you have a heat map over there. You get this other, in this other image, you're seeing that people will interact with edges of plates. People will interact with handles of drawers. And they will interact with like kettle handles and so forth, right? So you can get these kind of visualizations. And again, I think, it's purely coming from a human interacting with objects, and you can mine this kind of information. Yes?
So there's an affordance cluster around the blade of a pizza cutter. Is that?
Yeah, possibly.
Just wondering if that's...
right over here.
Yeah.
Yeah, you're right. So it's not very well localized, and we'll come back to fixing that issue. The reason why they're not very well localized is because I'm trying to make predictions for what I don't see, right? And so that's why they're not very well localized. We'll come back to try to fix it. Yeah. We have some quantitative results here. We are comparing against mask RCN trained on Coco. Whenever you compete with Ross, you always lose. And the right thing to do there is to join forces. So that's kind of what you're seeing over here. This combined model, So we have this data set where Mohit went in and labeled objects of interaction and where do people interact with it. So a bottle, there's really no preference on where you interact with. Plates, there is a preference that you interact with on the sides. So that's why if you have a very good object detector for these handled objects, which is how we filtered this particular predictions from this mask car CNN, it does well on COCO objects. It doesn't do as well on non-COCO objects. And when you combine it all, you get an improvement. And we get improvement over other past methods for doing this kind of a task. You can focus on non-COCO objects, and there you see a larger improvement. So mask car CNN will not do very well on those kind of things, whereas this thing will actually improve the performance. Okay. What else can we, so we can also output hand grasp. So what kind of a grasp is afforded by these kind of objects, right? So you're seeing like a tuna can kind of a thing over here, and a precision disk grasp is what works for this. And by just observing how people are grasping this object, you can actually learn this kind of behavior. So there's a parallel extension. So I'm showing you what are patches which, images which are responding highly to these kind of grasps that we are legal state. Yeah.
So when you trained this model, you said you would first run an object detector to find the hand, then you'd mask out the region. Within that masked region, you would predict, in a sense,
Try to predict where the hand is and what grasp.
And what grasp it is. But usually the hand is covering most of the object. So aren't you losing the most important? Like,
Yes.
How is this working without knowing that that's a box?
So I think the reason why this works is because of context. You are seeing, hopefully you're still seeing some part of the object, and that part can drive predictions for what you are not seeing. So this model has to do all of its job by the context, and I'm going to fix that problem in just a bit, right? Good question. Okay. So we can also tackle this question: what happens when we do the cupboard opens to reveal condiments? The way we are phrasing this problem is by learning state-sensitive features. So I want features which can distinguish between objects that are in different states. So closed cupboard should be different from an open cupboard and so forth, right? And the way we do this is it's like a feature learning setup. So in this case, we don't prepare data across a single frame. We prepare it across multiple frames. So you get the object of interaction, you get the what the hand is doing. You also get some information about the contact state, whether the hand is in touch with the object, contact with the object or not, where is the hand relative to the object, and so forth, right? So you characterize the hand motion and what kind of grasp it is doing. So you can prepare data this way, and now you can use some sort of self-supervised learning to actually do this. We were adopting SimClear at that time, along with object hand consistency. So I mean, SimClear, it's temporal SimClear, so it's not just SimClear in individual frames, but it's SimClear across frames. So the negatives actually come from other far away instances of an object being manipulated, right? So yeah, so the goal is to learn state-sensitive features, and if you have presumably some state transition has occurred on the object. So if you sample a far enough frame or like frame from another trajectory of the same object, you want to say that is actually far away, right? So that's this objective. What we are also doing is hand-object consistency. So you have the object and you have the hand, and the hand moves in a certain way, and we characterize that, and we say that the object features should be close to the hand features when the hand is time synchronized with the object. It should be far away from other hands in the data set, right? So the intuition over here is that if the object is in the same state, very likely you're interacting with it in the same kind of, the hand is interacting with it in the same way. So you can do this. This is open and closed. So how do we evaluate this? You learn features, and now you can try to understand whether these features are good for distinguishing tasks. So let's say distinguishing open objects versus closed objects. So this is again like some small amount of data that we collected, and we got improvements over past methods, specifically training for state classification on internet images. So you get some improvement on top of that. Improvements are larger when you have novel objects as opposed to when you have seen objects. And
Which one of these rows is Ross?
Which one of these rows is Ross? No, none of these rows is Ross right now. But you can ask this other question: what about GPT-4b? Right? I don't know yet.
How do you define state and objects that have state? Like if the other view of a hand, is this a different state or not?
Yeah, so that's kind of why we did not inject that into the feature learning part of it, because that's subjective. States depend on what task you're interested in doing. And so this is almost like a readout evaluation that, okay, let's say you were interested in a state, in a task, open and close. are your features good enough to distinguish between objects in these tasks, in these states? So this is done after. There's a feature learning. I'm doing feature learning. Hopefully it has learned a lot about how objects occur in different states. We are only going to be able to test certain subsets of these things.
But the set of features that learns open jar between closed jar are different from this view of a pan versus the bottom view of a pan, or
so maybe it is in the feature space. We tested it on like 10 categories of states classification that we came up with. Yeah.
It only sees open and close.
That particular classifier only sees open and close, but the feature space is hopefully richer than that. Yeah. Okay. Excellent. Okay, I'm going to come to some of your questions. Hands were useful, right? They tell me about affordances, right? I can see where what you can learn, what can you touch and so forth. And they're useful because they let me learn state-sensitive features, right? But none of this is, but they're also a nuisance in the way that was described, right? There's a data mismatch problem. I'm trying to make predictions for what I don't see. And when I'm actually going to run these state-sensitive features on a robot, the robot images are going to look very different, right? What if I told you I can actually delete the hands and generate this form of data for learning affordances and abstract out the hand and the robot gripper so that they are much more similar and you can learn a function that will transfer. So this is something that we did in a recent paper called Lukmano hands. And we are trying to factorize video frames into agent and environment representations. So there's a vector representation. You start with IT, which has both of these informations in there. What we want to generate is an agent image and an environment image. We're not doing this in feature space. It turns out, I mean, that's what we would have done if diffusion models did not work. But given that they work so well, we are doing this in pixel space, and that seems to work quite well at this point. The way we develop this representation is we have an agent segmentation model, which can segment out hands. So this is a hand segmentation model that we're using. And we have a video in painting diffusion model, which can take in video snippets and the mask and paint out the pixels in there, right? So this is our factored representation. So how does this work? To do this well, you need to be able to have strong priors to reason about, okay, what objects are continuous and what is the underlying appearance. But then you also need to pay attention to visual history, right? So in this case, what you're seeing behind the hands, I mean, a prior will not be able to do the job. But if you go back in time a little bit, you actually see there were oranges and not bananas. And so now you can actually do well at this, right? So this kind of a model, we are getting priors from a diffusion model trained on large-scale single-frame data. And we are leveraging visual history by adapting this model to attend to previous frames by cross-attention, right? So this is what this model looks like. I won't go into details, but the crucial detail is that you process, I mean, you try to copy as many of the weights as possible. You get these feature vectors, and there's cross-attention only at this layer, which means you can add conditioning to more frames without having to retrain lots of parameters, right? So this is kind of what we do over here, and you can see our reconstructions. They are better than single image reconstructions. They are better than, I think DLFormer was the state of the art for video and painting when we were doing this work. And this diffusion-based models actually do quite a bit better. Right, so we can recover these handles and these things. Yes?
Do you have any training data for this?
Yeah, the training data is by pasting hands. So you have hand segmentations in Epic Kitchen dataset. You paste them at random places, and you know the ground truth, and you do it that way.
Do you do it on videos or single images?
We do it on videos. So this is single image model, fine-tuned. This is with video data. So you can leverage, you can't get the oranges here if you don't look at the video, right? So yeah, so we are doing it with videos. It's actually past 4 frames. That's all that could fit on the A40s. Okay, so this is what pictures look like. You can delete the hand, we replace it with a dot. Here's another one where we have replaced this. This also works for these robot end effectors, or this proxy for a robot end effector. So you can paint them out. Yeah, here are some videos where there's no temporal smoothing over here. The flickering is because of multiple modes in that the diffusion model is trying to output. You could do better on that.
It's like magic.
Huh? Yeah, it's like the cutlery is floating around and such, right? Okay. Yeah, so you can actually also do this with robot videos. So this is kind of what you get. Now, how can we use this, right? So how do you use this factor representation? So we can go back to this affordance prediction problem where I was training a function on an image, and I can try to output where is the hand, right? So G is some function of the agent, and it could be where the hand is. It could be other things, what hand grasp it is exhibiting, and so forth. But the advantage now is you're actually going to make predictions on pixels that you're actually seeing. So hopefully it addresses your problem. We can also learn reward functions from this. So you can think of constructing a reward function which takes in the image and some abstracted out representation of the agent, and it predicts reward in this case, which is how far you are. You can actually do the same thing with the robot. So you need to come up with this function G and G tilde. We're not learning those. Those are handcrafted functions. In this case, it was so that you can imagine some retargeting that, okay, maybe I should get my robot fingers to be where the human fingers were or something like that, right? Yeah, so that's what you can do. So that's kind of what we have done. So this is a reward function purely trained on Epic Kitchen videos. And now you can use that to train policies for opening drawers. And this you can train a reward function. You can use it for optimizing behavior for opening a drawer over here. And what you can see is doing this the right way actually learns faster than other past work. You may have seen other people also painting out the hand, but they're not doing a factorization. They throw away where the hand was or throw away information about the hand. But to be able to learn that you have to grasp it, you have to actually approach the object. So knowing that the hand is going towards the object is useful, is necessary to learn the task. And that's what we are doing, what others are not doing, so that we can do it better. Right. Okay. Good.
One quick question. Your results show that if you go back one, so using the raw image as is and using the in painted version, it doesn't matter.
Yes, between these two. The reason is because, so this past in painting work from CMU, they were painting out the end effector entirely. So there's no sense of that when the end effector is going towards the object, you're losing information that you're making progress towards the task. Whereas if you keep this factorization, you keep information about what you have done so far, then you can learn better from it.
High-level question about this paradigm in general. So
Yeah.
today's diffusion models, single image diffusion models, they don't respect all the laws of physics. But let's say fast forward a number of years, diffusion models only generate realistic scenes. Is this going to work? Because you actually want to generate an image of a fork in the air.
Yes, I know.
So
good question. We've struggled with that quite a bit. This is actually true for all applications of diffusion models as well, where you are trying to generate content, a pink elephant, which doesn't exist on the internet, right? And the reason why those things work is some capacity is restricted in some model, or you do want it to go off distribution in interesting ways, right? So that's a more general problem.
yeah.
We were quite concerned as well that it will not generate cutlery hanging in air because you have never seen it, but it does do something. A very good question. Okay, now I'm really short of time, so let's see, 4 minutes. Okay, so can we do more? I think I have only shown you, somewhat like, the information that what hands are doing with objects is so rich. Why are we not doing more? Why are we stuck with like producing what grasps are being exhibited, not like what kind of a 3D hand pose I have? Presumably that will be more interesting because I can retarget that more easily into what a robot should do rather than like a grasp label, like prismatic grasp, right? We can do that, but for that, we need to understand the hand and objects of interaction. And I think that is kind of a missing piece. When we were doing these works, we did not find good models for 3D hand pose estimation or models for reconstructing objects that the hand is interacting with. Knowing both of these things is actually going to be important to be able to take this to the next step. So what we have done is we have actually worked on these two problems. We have models which actually improve the, we have tackled this problem. So Frank Mocap is a popular past work for this. And if you run it on challenging settings outside of lab settings, this actually doesn't work. Fingers are not curled enough. They look kind of okay, but they're not okay. And so we have some work where we try to improve it. And at this point, I'd like to know how much. So I have to end sharp at 2:30, in which case I'll skip this and just conclude the talk.
Yeah, it's probably best to plan to it.
So I'm happy to talk about these offline. There was a nice computer vision nugget in there, but I guess you'll have to talk to me for it. Yeah, so I think what I tried to show in this talk was essentially this idea of this triangle where information can flow at multiple different levels. I showed subroutines and affordances. I showed you can learn dense reward functions and derive behavior from that. I showed this for navigation. I showed some work on how you can learn common sense about objects and places. where can you interact with the scene, how do you interact with the scene, and different states that objects exist in. What I would have showed you, which I did not, I showed you, also human behavior analysis, right? So dealing with this embodiment gap. I guess what I was going to show you was 3D hand pose estimation from images to getting good hand pose, which I did not, and also work on reconstructing objects of interaction. So obtaining 3D reconstruction for objects which have been occluded by the hand, right? But we need also the third piece of this triangle, which is robot behavior generation. And I've done a bunch of work on this, and maybe this is what the audience was expecting I'll talk about, but I did not. So we have work on whole body mobile manipulation, where we have these stretch robots which are going around in UIUC, opening doors and cabinets, and this is not using the reward functions we have learned from videos. This is some other methodology, but we have work on like getting these physical platforms to do things. Illinois has lots of cornfields, as some of you might know. So we have robots which are driving down cluttered environments, in this case, trying to go down under the canopy to phenotype these soybean and corn plants.
Yeah, that's not a cornfield.
That's not about this is soybean, yes. We also have manipulation of deformable objects. So in this case, we are trying to see behind leaves. So this occlusion problem. So we're interested in manipulation of deformable and articulated objects in different ways. Yeah, so I think with that, I'd like to thank you all for your attention and leave some points for discussion open while I take questions the rest of the time. Thank you for your attention.
We haven't seen yet. What is this toilet seat that we haven't seen yet?
This is the earlier version of this mobile manipulation project, which we were trying to articulate objects. So I can maybe try to pull it up.
From a static object. Can you open something and sort of render what's behind?
I think maybe this is the picture which draws the. I guess
To me, that's sort of the most exciting recent work.
this one, right? This got put in some DARPA grant presentation, and then we were like, does it put it down as well? Yeah, but
It's actually a key missing piece in my book. No, seriously, because like when you manipulate, how does it look like after that? Tells a lot about how you train them.
yeah, yeah. I mean, what we were looking at was getting the robot to produce trajectories which get the end effector to follow a precise trajectory. Yeah.
Well, good that we didn't ask a lot of questions, so you get to finish your talk.
Thanks again, sir.
Yeah.